Beneath the manicured New Jersey fairway, a hard, dark layer of sediment interrupts everything geologists expected to find. Below it, concentrated platinum group elements, charcoal, and signatures of extreme heat. Above it, that signal disappears. The boundary dates to approximately 12,900 years before present, the exact moment something violently reversed the warming climate of an entire hemisphere. Scientists have spent nearly 2 decades debating what could leave that kind of mark in the ground. The anomaly hidden beneath this golf course may be part of a pattern that still has no settled answer. Standard textbooks reconstruct the post-glacial climate from ice cores, pollen, and lake sediments, presenting a gradual transition. But you will search scientific literature in vain for a verified late Pleistocene anomaly directly beneath a New Jersey golf course. This specific scenario is a composite reconstruction of very real regional debates. The hard science is far more elusive. To prove such an anomaly exists here, you would require secure stratigraphic context, documented sampling protocols, and peer-reviewed testing. Investigating this gap between neat textbook models and raw physical evidence is why you should subscribe to this channel. To understand what lies beneath, you must first look at the ancient terrain that preceded the modern fairway. 14,000 years ago, the colossal weight of the Laurentide ice sheet was retreating northward, leaving behind a scarred, rapidly reorganizing geography of proglacial lakes, floodplains, and braided river networks. As massive volumes of glacial meltwater carved new paths across New Jersey, they deposited thick sequences of fine-grained silts, gravels, and clays. During the Bowling-Allerod warming interval, a comparatively stable climate allowed rich organic material to accumulate in quiet wetlands and ancient lake margins, forming dense beds of peat. Forests of spruce, birch, and cold-hardy conifers gradually colonized the damp terrain, initiating a slow vegetational shift and creating a humid post-glacial wilderness. This was a world of giants. Through these marshy corridors roamed herds of mastodons, mammoths, wild horses, and ancient bison, their heavy remains sinking into the water-saturated clay. Standard geology expects you to find this predictable sequence beneath any modern open space, a slow, gradual record of ecological succession, step by step, from glacial runoff to mature forest. But nature rarely adheres to the neat, linear chronologies of standard textbooks. Around 12,900 years ago, the post-glacial warming trend shattered. You are looking at the onset of the Younger Dryas, an abrupt 1,300-year freeze named after Dryas octopetala, a cold-hardy wildflower whose pollen suddenly chokes the sediment until 11,600 years before present. This boundary poses an unsettling question. Does this buried layer record an internal Earth system transition or a high-energy event from above? Here, a second mystery is layered onto the cooling. Within this narrow horizon, you find a synchronized alignment of rapid vegetation collapse, intense fire residue, and severe megafaunal stress. But you must distinguish a regional faunal decline from a proven local kill site, and a concentrated depositional band from generic wildfire ash. The alignment is highly suggestive, but it is not yet proof. Into this unstable terrain walk the region's first human inhabitants, mobile hunter-gatherer bands tracking resources across a shifting mid-Atlantic geography. To find their physical traces, you must look to regional anchors like the Shawnee Minisink site in the upper Delaware, where diagnostic fluted stone points confirm a Clovis-era presence. Modern Lenape history belongs to a much later epoch. These early groups faced a far harsher wilderness. As habitats shrank and forage zones vanished, these hunters followed highly stressed animal populations. Whether climate-driven habitat loss, direct human hunting, or a lethal combination of both pressures drove the megafauna to extinction remains unresolved. Survival was a calculation of roots, prey, and water. The convergence of separate physical signals within one narrow stratigraphic setting is what makes scientists uneasy. Matching timing alone cannot establish causation, but when distinct sedimentary changes align, coincidence fails as an explanation. During drainage regrading on an anonymous fairway, a ground supervisor struck an unusually hard, dark contact that behaved differently from ordinary loose fill. The crew dubbed it the Black Pan, an uncredited maintenance shorthand for a barrier that resisted standard machinery. A composite geologist evaluated this boundary, logging depth, preserving the layer contact, and sampling multiple points while documenting the construction history to rule out modern grading contamination. They analyzed the sediment structure, mineral particles, and microscopic biological remains to estimate its potential age. Yet you will find no verified, course-specific discoverer, official measurement record, or formal report for this site. The physical evidence remains an illustrative reconstruction of real regional debates, waiting for systematic validation. Instead, you must look to the actual scientific publication that gave this broader dispute its formal name. In 2007, a landmark paper by Richard Firestone and a team of international collaborators publicly advanced what is now known as the Younger Dryas Impact Hypothesis. They proposed that one or more cosmic airbursts or impacts from a disintegrating comet struck the Laurentide ice sheet, triggering massive wildfires, ecological collapse, and sudden hemispheric cooling. This was a sweeping global claim, completely independent of any localized New Jersey fairway. It sought to explain a planetary transition, transforming a debate over regional sediment layers into a high-stakes controversy over a cosmic catastrophe. But a formal hypothesis is not proof. To evaluate this anomaly, you must put it to 5 rigorous physical tests. First, look at the stratigraphic order. In an undisturbed profile, sediment layers accumulate sequentially, but a sudden contact can form through rapid flood deposition or an abrupt environmental shift. For this to represent a genuine geological event, you must trace a narrow, laterally continuous horizon across the site, rather than isolated patches of dark material. Skeptics rightly point out that modern grading, drainage cuts, imported fill, and heavy compaction can easily mimic these ancient boundaries. A sharp layer proves an interruption. It does not identify the interrupter. Second, consider the absolute dating. You must combine accelerator mass spectrometry, or AMS radiocarbon, with optically stimulated luminescence, which measures when quartz grains were last exposed to sunlight. Secure chronologies require strict agreement between individual organic samples, screened bone collagen, and adjacent quartz. However, bioturbation and root penetration frequently introduce younger carbon, while older, reworked peat can artificially inflate the age. A number on a laboratory report is not the same thing as a secure burial history. Third, analyze the chemistry. You are searching for platinum group elements like platinum and iridium, along with microscopic iron-rich spherules. A true anomaly requires a highly concentrated, narrow spike that stands out from normal background levels. Critics argue these metals can accumulate through volcanic ash, mineral weathering, or even modern industrial contamination. Without independent verification of shocked quartz or diagnostic mineral deformation, the chemical case remains incomplete. The particles may be real, their origin remains the argument. Fourth, examine the biological remains. Charcoal, pollen, and spores record past fires, vegetation, and the presence of megafaunal dung. A synchronous ecological collapse suggests a major crisis, but local wildfires, localized droughts, and natural forest succession can produce identical patterns. You must not mistake these biological fluctuations for a verified bone bed or an active Paleo-Indian hunting site. Biology can reveal that the landscape changed quickly. It cannot, by itself, name the cause. Fifth, apply the regional test. Proponents point to distant comparison sites like Murray Springs or Lake Hind, yet visual resemblance is meaningless without independent sampling and secure, separate chronologies. A pattern becomes powerful only when it survives distance, different sediments, and independent laboratories. Evaluating these 5 tests requires distinguishing textbook models from raw material evidence. If you want to see how scientists separate familiar Earth system processes from signatures that survive controls, subscribe to this channel. Mainstream climatology attributes the Younger Dryas to a massive freshwater outburst into the North Atlantic, likely from Lake Agassiz. This freshwater lowered sea surface salinity and density, weakening the sinking branch of the Atlantic, meridional overturning circulation. Northward heat transport collapsed, initiating abrupt hemispheric cooling without cosmic intervention. The climate changed, but the trigger remains in the water. On a highly modified terrain like a managed course, human activity complicates the stratigraphy. Decades of grading, drainage installation, imported sand, and heavy compaction alter the soil profile. Fertilizer, pesticide application, and maintenance excavation create artificial pathways, while bioturbation and root penetration move particles and carbon vertically. Metal tools, industrial dust, and laboratory handling introduce contamination, producing old carbon reservoir effects and skewed radiocarbon dates. Ordinary flood deposition, routine wildfires, and pedogenic processes can easily explain these patterns. Skeptics argue the proposed markers are neither globally synchronized nor consistently reproducible. The ground itself has been rewritten. You test physical mixing by comparing the course profile to untouched adjacent zones, looking for continuous drainage traces and soil horizons extending outside the fairways. You control contamination through procedural blanks, background samples, and blind isotopic replication across independent laboratories. You resolve old carbon offsets by dating short-lived botanical samples, screened bone collagen, and quartz luminescence at multiple depths. You test wildfire theories with particle morphology, mineral deformation, elemental ratios, and distribution outside the burn environment. You counter localized deposition arguments by identifying identical layers at distant sites. The hardest observation to explain conventionally remains a repeated, tightly dated, multi-proxy horizon in separate, undisturbed environments. This establishes a regional event, regardless of the impact mechanism. Under the quiet turf, the ancient soil remains awake. If a buried layer under a golf green hints at a sudden shock, what does the hidden clay beneath Morris County's Sugarloaf Hill reveal about the forces that reshape the ancient world? Subscribe to the channel to explore these hidden fractures in our climate story. To move past local contamination arguments, you must evaluate undisturbed natural archives. A layer locked within a pristine peat bog, ancient lakebed, or active floodplain is far harder for skeptics to dismiss than a highly modified Gulf fairway. Here, a strict hierarchy of evidence applies. Shared timing across different sites forms the base layer of proof. Repeated proxy combinations build the second tier. A shared physical mechanism stands as the final, most demanding test. Initially, the impact hypothesis relied on a simple cosmic strike causing instant planetary fire and immediate freeze. Today, the model is far more detailed. It incorporates multiple regional airbursts, secondary wildfires, disrupted river systems, and severe ecological feedbacks. This updated model links geological and biological data more cleanly, but its moving parts require many more unproven assumptions. You must accept a hard reality. No verified late Pleistocene anomaly has ever been proven beneath a New Jersey golf course. While the cold Younger Dryas interval itself is a secure geological fact, its exact trigger remains intensely debated. Mainstream data heavily favors circulation-based, internal Earth system models, yet proponents of an impact point to persistent biological and material anomalies that resist easy explanations. Researchers like James Holliday, Mark Meltzer, and Catherine Suravel advocate for rigorous methodological caution, highlighting instances of mixed replication. Ultimately, the scientific community lacks any single, conclusive impact marker accepted across the entire field. Consider the ultimate convergence, a preserved boundary, sudden ecological disruption, and the simultaneous disappearance of giants and hunters. To understand how such forces operate without leaving a scar, you must look to the 1908 Tunguska airburst. In that Siberian wilderness, an atmospheric explosion produced searing heat and massive shock waves, flattening 80 million trees without leaving a conventional crater. This event demonstrates physical plausibility rather than direct evidence of what transpired in New Jersey. Over 12,000 years, soil formation, bioturbation, and sediment mixing complicate the preservation of these fragile markers. Could separated, undisturbed sites share this synchronous signature without a common regional cause? Beneath the manicured green, The dark boundary remains undisturbed. We play on a surface of engineered certainty, yet the Earth's deepest scars lie just inches below. Next, we uncover what Morris County's Sugarloaf Hill reveals about our fragile climate.